You know why? That's odd. All right, y'all. So, like I was just saying, we're going to get into applications of parametric equations, and want to start off with a skateboarding example. It takes me back to my days of skateboarding. Young Nate busting up his knee skateboarding. Kevin is skateboarding when he hits a ramp to make a jump. The ramp has a 30-degree angle. Kevin hits the ramp at a rate of 36 feet per second. We want to find the horizontal and vertical motion without the effects of gravity, to start us off. So suppose Kevin is skateboarding in space and is not affected by gravity. How far up will Kevin go after 1 second? How far will he have risen after t seconds? Can you guys talk about this in your groups? See if you guys can't brainstorm then. Jump on a whiteboard if it behooves you. How far up? How far up? How far up?
T plus 2 seconds. T plus 30.
How far up? How far up? Not how far.
2 seconds times 30 seconds.
Not how far. How far up? Not how far. I'm not going to say over either because that's different. Not how far diagonal. Yeah, not how far vector to diagonally like that. How far up? No, that's my wrong. How far up? How far up? No trick. How far up? How far up? Vertically. Right? How far up? All right. How far up? How far up? And to sort of debrief, hey Maggie, to debrief a little bit, and just kind of get a sense of how we're understanding this. How far up? Why isn't it 36 feet? Why is it not 36 feet? Why is it not 36 feet? Why is it not 36 feet? I'd love for it to be 36 feet. What is 36 feet? What is 36 feet? What is 36 feet? What is 36 feet? Yeah, let's just say after 1 second of traveling, and if you're going 36 feet per second, then you've gone this direction 36 feet. You've traveled 36 feet, kind of in terms of the actual distance that you traveled, if you're going 36 feet per second. Does that make sense? If you're going 36 feet per second that way, then after 1 second, you would have traveled 36 feet this way. You would have traveled 36 feet this way. But Kevin hitting this ramp is not traveling 36 feet this way. Kevin's traveling 36 feet that way. 36 feet that way. So how can we figure out the vertical distance that Kevin has traveled after 1 second? He went 36 feet this way. How do we figure out this vertical distance? Talk in your groups. Talk in your groups. Talk in your groups. Talk in your groups. How do we figure out this vertical distance right there? Not this one. That's 36 feet. That. Teamer, do you want to join those guys in the back? Go ahead, man. Yeah, go ahead. Hey, Luca and Zach, Teamer's coming over there to join you guys, so we have some conversation partners. Thanks, Maddie. Man, I'm hearing lots of great stuff.
Well, it can't be if that's like the side. The side. Yeah. One of those like. Right. I'm sure you can also like type that design. Part of me thinks like, and this is probably wrong, but you know how it's like the opposite angle corresponds to the line?
All right, y'all. There's so much good thoughts. Can we bring this together and say how do we travel that? How do we know how far up we traveled? How do we know how far up we traveled? Yeah, Drew, what you got going?
We can use the ratio to the side of 30, 69 triangle to figure out the bottom side.
Oh, well, here we want to figure out
That side.
this side, the opposite side, maybe.
Opposite side.
Mm-hmm. And can you tell me the formula or the equation that I would use to do so?
X. Oh, you do 36 divided by 2. The hypotenuse is 2x. The opposite side is x, and the bottom would be 3. Yeah.
Amazing. So you're remembering SATs? Is that on your mind at all? A little bit with those 30, 60, 90 triangles. And you know, and it sounds like Drew's remembered that 30, 60, 90 triangles have a special pattern. You said the shortest side is half, you said?
Yeah.
And the other side is it root 2 over root 3 over 2?
It would be 18 times root 3.
Over 2. Or 18 times root 3?
Yeah, it's 18 times root 3. Because the hypotenuse is 2.
Oh, yes. Yes. You're right. Haven't taken the SATs recently. Nice one, dude. You got it. Now, that's if we know our 30, 60, 90 triangle ratios. Does anybody know where the 30, 60 triangle ratios come from? Oh, good. Unit circle? I was even thinking that I can tell I've totally brainwashed you. That makes me happy. I was thinking even this is a triangle. We can think about geometry. SOHCAHTOA? The sine of 30 degrees is equal to the opposite over the adjacent. And so we can write this out as, let's say he hit the ramp at like 26, or angle 26 degrees, right? So then we can write here that the sine of that angle is equal to our missing opposite side over our hypotenuse. And now I'm hearing like unit circle, sine of 30 degrees, y'all. Sine of 30 degrees. Good. And if you don't mind me doing 2 steps on 1, 36 times 1/2, that's okay. Nice. So, and you know what, actually, I'm going to put y. You'll see y here in a second. I'm going to have my variable y. It doesn't matter what my variable is, as long as my variable is opposite. You might be able to imagine y at the outset. So our vertical height, at 1 second, our friend Kevin, our boy Kevin, is going to have gone 18 feet. 18 feet. So far, so good. And that's after 1 second, but after t seconds, if he goes 18 feet in 1 second, how far is he going to go in 2 seconds? 3 seconds, 4 seconds. And so our formula is going to be 18t. So ignoring the effect of gravity, when Kevin hits this ramp going 36 feet per second, he will be going up initially by 18 t. Oh, yeah, no, we're ignoring the effects of gravity. So going up by 18 t. Imagine no gravity. 18 t. All right. Can you now take a second and, using the work that we just did, calculate how far Kevin will travel in the horizontal direction after t seconds. In the horizontal direction. We already did some of this work, but if you can, build out the trig, because what if it's 26, right? What if it's now we're not thinking about up, we're thinking about over. We're thinking about over. So think about how far Kevin travels over. Yes. Nice work. You guys are picking up on the patterns here. And I'm hearing it. You set up the equation, the adjacent side over the hypotenuse. So the cosine of 30 degrees is equal to x, the horizontal direction, over 36. Cosine of 30 degrees. Happy you did all those trig values quizzes in the fall. Fine. Happy's a strong word. Can't think of a better word right now. And you all get 18 root 3 after t seconds, 18 root 3t. Exactly what Drew pointed out up above with this 30, 60, 90 triangle, right? So now, and let's highlight this. Let's capture what we've gotten so far. Kevin hits this ramp going 36 feet per second. We know that his vertical position will be given to us by 18t, and his horizontal position given to us by 18 root 3t. See what's happening here? And now it's time to add in the effects of gravity. The effects of gravity. You may recall from a physics class or earlier in this class, the gravity constant on Earth is negative 16t squared. I don't know why I asked John Garnavikas. I have no idea. It's just how it is. And so which of those two equations is that gravity going to affect? Remember we did the nickel example, right? And the gravity affected that y coordinate. It does not affect our x coordinate. So go ahead and let's factor that into our situation. So now we have that y, which is that vertical height, now being affected by gravity. So now you have two competing forces going on. You have like this 18t force, this like momentum going up, but at the same time gravity is pulling you. So it's like these competing forces that are going against each other. Hey, quick polynomial review from Algebra 2. Think about this in terms of terms. You have it's a binomial. You have one term and two terms, two unlike terms. What kind of function is the gravity term in this case? What kind of function is it? Quadratic. It's a quadratic. And what kind of function is the momentum term? Linear. And if you have a quadratic that's pulling you down and a linear that's pulling you up, which one's going to win in the long run? That's why we come back down to Earth. The quadratic, as our t's get bigger and bigger and bigger and bigger and bigger, that quadratic term is going to get more and more and more and more negative. The momentum term gets bigger and bigger and bigger positive, but the quadratic gets even bigger and bigger negative. And so if you add a bigger negative with a smaller positive, that's going to bring you back down eventually. It's going to bring you back down to Earth eventually. More on this when we do limit analysis. So more on that kind of ideas when we do limit analysis. All right, last thought here. Let's just say that the ramp that Kevin hits to go 30 degrees to go 30 degrees. See that 30 degrees? Let's say that ramp itself is 3 feet high. Talk in your groups. How does that change our equations? How does that change our equations if the ramp, we start the time, we start t, the second that Kevin goes flying off the ramp when Kevin's airborne, say that's when we start t, how does the 3 feet change our equations? How does the 3 feet change our equations?
No, I think it's the ramp. Instead of turning to like the whole equation. Instead of the ramp. Well, it's not trying to gravity.
Is the 3 feet having to do the horizontal position or the vertical position? And how?
Yeah, more high
Anybody want to volunteer? How does it? How does the 3 feet factor in? How does the 3 feet factor in? Is it horizontal or vertical? And are we adding 3 feet or are we subtracting 3 feet? Perfect. Plus 3. That's it. And so at the end of the day, we have our 2 parametric equations. This is what this has been building to this entire time. We have our 2 parametric equations. We've built our 2 parametric equations from Kevin's antics. And our 2 parametric equations are as such. We know that Kevin's horizontal height will be given to us by that function. X is a function of t. The x position, the horizontal position, will be given to us as a function by t. Some sort of linear function with a coefficient of 18 root 3. And his vertical position will be given to us by this quadratic. Okay, can you guys take out Desmos? Let's get this in plotted and see what this thing looks like. Please plot these parametric equations. Pro tip on Desmos, SQRT gives you square root automatically. Baller. If you type in SQRT, so you don't have to go searching, like 18 SQRT gives you the square root function. Make sure not to square root your t in the process, right? You have to click over with your arrows once to get the t from underneath the radical. What's that? Make a 16t squared. What was it? Plus 18t. What's that? Plus 3? Cool. And that looks pretty good. I mean, you can just see your Kevin's motion, right? You see Kevin's movement. Starts off 3 feet in the air. Whee! Takes off. It's going up and up and up and up and up. And you can see that his initial ascent in the air is really fast. You start to see it starting to slow down here. Let's check out what happens to Kevin, our friend Kevin, at that point. And it's going up. It's starting to flatten out. Starting to flatten out. Starting to flatten out. Starting to flatten out. Very good. And he reaches his height, his peak height. We know parabolas will give us like some sort of vertex, a max. And it's going down. And it's going down. Oh, where does he land? What? Pauses midair. How does that work? Sorry? Oh, the plus 3. Is that what 3 is right here somewhere? Yeah. Why does he just stop midair? That doesn't make any sense. Ah! Sorry? It's only been 1 second. He's gone that far in 1 second already. Let's think this further than 1 second. Let's make this at what? 2 seconds? Oh yeah, there it is. Whee! Boom! And he collides into the ground. It's like an anime sort of. The building collapses around him. All right, so it's kind of hard to tell. I don't know. Maybe make that t is equal to what? 1.5? Too much. What? T is 1.3 is a good one. 1.3, close. 1.27 says Zach. Oh my gosh, did he land? Oh my gosh, imagine how tantalizing that would be. Wow! And he's like hovering. Whoa, dude, what? It's weird. 1.2 what? 275. Ooh, oh, that's a hard landing. 272. Oh, feather landing. Feather. Oh my God. No, this is like, he's like literally, he's like, am I on the ground? Okay. I think we made the point here. The parametric equation is really helpful for helping us to answer this question. When does our friend Kevin hit the ground? But using a graph, we can see here that we're kind of messing around with this, and but we can't quite be sure when he hits the ground. Maybe we should do so algebraically. So if we want to answer the question, when's Kevin going to hit the ground? How long does he remain in the air? How do we use our parametric equations to get at that answer? How do we use our parametric equations to get at this answer? If we want to figure out when does Kevin land, we did a pretty good job of approximating 1.272, but even then, sorry? This is a great observation. We will know that Kevin hits the ground when our y location, our y coordinate, our y height is equal to, all right, go ahead and write that down. So let's see here. We want to solve when Kevin hits the ground, how long is he going to remain in the air? So let's see here. We have, we're going to use our y. We're going to use our y equation. And what we're really curious to know is when is our y coordinate equal to, and now you are right back into Algebra 2 land, right? Solving quadratics. Can you guys please solve this quadratic for me? We know it's not factorable, right? Because what we've discovered just in T's. So we know it's not factorable. When a quadratic's not factorable, we have to use the quadratic formula. Anybody remember the quadratic formula off the top of your head?
-a plus or minus the square root of
squared minus RAC.
What in the which category?
Horror slasher zombie poltergeist math movie. I'll give you guys the pitch right when class ends. I want to make a movie. I want to make a horror movie. Yeah, exactly. Perfect. That's what I was going for. I've got a movie in mind. You guys direct it and write it. My idea, 51% me, 49% you. We'll make it killing. Pun intended. All right, quadratic formula. I love you too. Hey. It's fun. It's fun. It's good. All right, get that algebra done. It's the best part about pre-calculus because it's an algebra 2 task. You guys do it. Just tell me what you get. We're going to know that one of them is going to be negative, right? Because it's going to be over here in the negative. We don't care about that one. That one's called extraneous. It's going to be an extraneous solution. You guys remember that word from algebra 2? You guys thought that people were just... Last year, Marian's making up that word. There's no word extraneous. And then I say it. Make it like that. Make one. I don't know how yet, but we'll figure it out. Just a great bottle. Can't believe this bottle is going to the recycling bin.
No, it's just the
51% me, 49% you. We're going to make a killing, Katie.
writing and producing.
I'll show up occasionally, micromanage obnoxiously, and then leave.
You could be like, thank you.
Sound good? I'll show up occasionally, tell you guys all what's going on. It's just definitely not my vision. And figure it out, and then I'll walk away. Sounds like a great, healthy work environment. Anybody got those numbers yet? No, not yet. Looking for numbers. We know it's going to be 1 point something. We know it's going to be like 1 point. We know it's going to be 1 point like 2. We got the exact number. It's probably going to be 1.27 ish. Got it? No, come on, knock this out. You guys all remember how the quadratic formula works, right? We're squaring the 18, opposite 18, plus or minus the square root of 18 minus 4 times negative 16 times 3. Oh, 2 times negative 16. Nico and Neil will tell you this is how AP Stats operates. I point them on my heart. You guys calculate. I just wait for someone to give me an answer. That's what happens, right? That's like most class. Everybody's like, "Oh, you're gonna do it. You're gonna do it." There's some things here, right? Like you gotta be. I mean, you guys are pre-calculus owners, so I think you guys shouldn't have any problem with this. But we got square minus 4ac. Point what?
I got 0.147363543.
And then it's 2.
That's one answer. So.
0.1.
But 0.14 is already bigger than what?
Yeah, that's
So
I.
He crashed it. Good job, man. That poor kid. Poor Kevin, man. Had a rough journey on a skateboard.
All right, y'all. All right, let's do this. All right. Yeah, Lord Almighty. Negative 18 plus or minus the square root of 18 squared minus 4. This is tricky for some algebra students. Times negative 16 times 3. That number is going to be positive right here, right? Okay. All over 2 times negative 16. So that's going to be negative 18 plus or minus the square root. And the way I tend to do this is I do the whole discriminant. You guys remember that? That's the whole thing under the radical, the discriminant. I do that all in one shot. So that's going to be 18 squared plus, because it's going to be plus a 4 times a, which is 16, times c, which is 3. Oh, but I made it plus because subtract negative.
Oh, okay.
So subtracting a negative. So 516. So negative 18 plus or minus 516. That's how I do it when I teach it to kind of take it in these stages. All over negative 32. So the square root of 516. I have no idea. That's not a perfect square. 516. 22.715. So it's negative 18 plus or minus, what was it? 22.716. All over negative 32. So what's that? 4.716. Now it's going to be a remainder. So we'll do negative 18 plus that number. And then divided by negative 32. All right, so that's that negative number, negative 0.14. And that makes sense, kind of. It's going to be a negative number because that means behind it will give us this landing. Like if I take this and make this negative 0.14736, yeah, there. See how that takes that down nicely if we make that t the other way? But in our situation, there's no such thing as negative time. There technically is. Negative time is the time before you start the stopwatch. That's what negative time is. Like, so just before you hit 0. But the one that we're interested in is the minus. Look at there. That's it. 1.27236. That's it. And that's what we wanted. I'm going to put both solutions down because this is a 147, right? 0. Come on, glitchy. 147 or 1.2724. 2724. And at this point, we circle this, or I mean not circle, but cross it out and write extraneous. Extraneous. And we highlight our solution. So our boy Kevin's going to remain in the air for 1.2724 seconds. That's not that long. Kind of long. 36 feet per second sounds kind of fast. 1,000. Long time? All right. Time for part 2. How far does Kevin travel horizontally in that time? Talk in your groups. How do we use what we've currently discovered in order to calculate that number? How do we use, or how far does Kevin travel horizontally?
The web-based platform.
Like, I don't know. Like, again, and, but no, to your point, though, Zach, and I'm glad you bring that up. If this was NASA, and we're dealing with such sensitive equipment, and you land like that, that's when I got this kid who was level 1. They just went around for years like heads all the time. They want to deal with like decimal level 1, right? Can we just run it? So we can. Well, I'll tell you one thing, if you're managing someone's money sometime, and you keep on mopping up, have you ever seen that show Office Space? The whole premise of the movie Office Space is that he's working as an accountant in the lamest, most boring office in the entire world. It's an accountant. And he's got a meaningless job. His life sucks. And what he realizes is that all the calculations that are happening with money, they get rounded to the nearest cent anyway. So all of those like fractions of cents, like a tenth of a cent, a hundredth of a cent, like no one's even keeping track of this money. So he came with a computer program to take those tenths of a cent, hundredths of a cent, and put them into his private bank account. And what could go wrong? What could go wrong? Hilarity ensues. He wakes up the next morning, and this big financial institution does so many transactions a day. He's got like $800,000 in his account after one night. Just because if you take tenths of cents off hundreds of millions of dollars, that's what's going to happen. Same thing there. So hilarity ensues. Jennifer Aniston, isn't it? Like from way back in the day. You guys in the 90s? Office Space. Yeah. Great Jennifer Aniston movie. Lots of flair. All right. So let's see here. I was listening in, and you guys were correct. If we want to figure out how far he's traveled horizontally in that time, then we take that time. That time is essentially the time that he lands, and plug that into the x of t function. And you'll have 18 root 3 times 1.2724. I assume that you guys have crunched the numbers and got 39.6. Future AP Stat student here. I just asked and you guys calculate something for me. 39.6. 6 what? 669 what? Feet. Perfect. And that does seem pretty far. Traveling 40 feet. That seems kind of crazy. There it is. So, in short, parametric equations are really an essential tool for calculating these sorts of scenarios. The word for these sorts of scenarios are projectile motion. This entire time we've been working on projectile motion. Projectile motion. Whenever, when you guys at the end of the year, we're like, man, let's go TP Nate's house. Yeah, we just got to throw TP rolls in my huge tree. I'm like, no, you kids, get out of here. Like the function that, we calculate the trajectory, the projectile motion of this wire balloon's name. Like you guys are firing them off me. This is the function that would capture the physics of that. It looks complicated, no? It looks complicated, but we just did it. Let's break it down. That's how we'll wrap up today. What we've got going on is, and it starts, and this is a great algebraic tool, is to think about the formula in terms of its terms. In terms of its terms, and think, what does each term do for the formula? Well, this first term is like the horizontal momentum. That's like that horizontal momentum term, horizontal momentum. And if you remember how we calculated that horizontal momentum, that 18 root 3, we took the cosine of 30 degrees times 36. That's what this is. V is that velocity. V is that initial velocity. So we have our initial velocity times the angle, times the cosine of the angle of liftoff or launch. That's what that first piece means. 18 root 3. That's the 18 root 3 t part. If that helps you, just write that up here. That's the 18 root 3. That's the 18 root 3 part. It's 18 root 3 part. 18 root 3 t. 18 root 3 t. Function of t. And that second term, we're always going to have, this is our, we didn't have it in this case, but this is our initial horizontal position. Like when the faculty compete against you guys in tug of conflict, it's supposed to start right in the middle, but I notice what you do. You give it a little horizontal tug just to get us off our bearings. I noticed. Don't you think that we don't notice that? And our horizontal position in tug of conflict should be 0. Should be right down the middle. But don't you play coy with me? I know what you guys do. I feel a little tug this way. And so that initial starting spot, that initial horizontal starting spot, is something other than where it should be. Then you'd factor that in there. Yeah. All right. For the vertical location, we have 3 terms. There's 3 components. There's 3 terms, 2 of which are the same. We have our initial vertical. Just like we have our initial vertical, our initial horizontal, we have our initial vertical. That's where Kevin, that's at the height of the ramp that he takes off at. We have our, I guess we'd call it our vertical momentum. That's the 18t. So nothing funny, exactly the same as the horizontal. The horizontal and the vertical look almost identical. Only difference there is the sign, right? Because the opposite over hypotenuse, right? That's the vertical. The sine would be the opposite versus the cosine. God, this is such an easy set. I'm like just breaking down formulas and telling you guys to calculate. Exact. Because it's not how break down the formula. Now you calculate. And the only other thing that is comprised in that vertical location, yeah, you guessed it. We're not on the moon. Gravity. As long as we're on Earth, that will be negative 16t squared. Go to Jupiter, negative 1,000 t squared. I don't know. No idea what it'd be, right? The force on Jupiter. Is Jupiter a gas giant? Like it is. So can you even stand on Jupiter? Yeah. Not because of the gravitational crushing. Happen. All right. Get there. The air to start off with. All right. Sounds good. 8:46. Oh, yes. We still have a few more minutes. Can you guys spend the remainder of your time working on number 2, which is an application? And we'll leave it there. I'll come around and help out. You guys tackle number 2. Where's Kennedy? The golf championship.
Okay.
Jared Shane. Where's Jared Shane? Any golfers in here? You tell us and how realistic this is. Okay.
Olivia.
So is the initial horizontal position?
Pay attention to your units, right? God, physics. I'm so glad I'm not a physics teacher. You gotta pay attention to units, feet, yards. Careful. Careful about your units, the feet and the yards. It's annoying, I know. Trust me. Careful about your units.
45 feet is that not 3 yards? I mean, 15 yards.
Oh, I hate that. Yeah.
Careful about your units, everybody. Feet, yards. Make sure that everything's in the same units.
It's asking for.
The velocity.
I think I can want a picture of scenario.
Draw a picture. It's great. Me too. Draw a picture, sketch.
That could be great.
Complimenting on my art later.
Oh, she has to go
Over club.
I think it's time.
Oh, now I understand.
Tree. Careful, Amy. I'm coming for your job. Clear tree.
Oh, so we don't.
Onto a green. Green. Match. She's 100 yards in front of the green. 100 yards.
And it's not.
She's 40 feet high. 30 yards away from position. From the front of the green, I should say this.
Wait, no, isn't this your 30 X and then 100 yards from where it is together?
38
I
lob.
thought strikes the ball from the ground before something, and then the velocity point should be 30 yards. That's what I was looking at.
I think it's this. I think this is
100,
what I was looking back.
100 and
It's 34 yards.
I thought
102.
it was like
1 second.
but we gotta change
It's 34 yards, so 102 meters.
Come on, Dad. Careful, I'm gonna come for your job. Here we Donna. Charge teacher.
Alright, this is 15. Oh, so this makes this 1, 2.
We're an interpreter style.
15. Yeah, 15 yards. I just changed it. Oh, it's 3.
I don't think that's. I think that's what's hard to use.
Look, if you guys looked at it, it's like,
I
it's not very
just
long.
I can't find what the shot is.
That you said it already?
So we need to figure out what the measurements of the.
Hey, that's not
Very good stick figures. No. It's a metaphor.
40 feet and it's
Symbol.
30 yards.
Something.
That's how far away the tree is from the position. We need to figure out what she is doing. Or the VO in front of the green.
Nate, who holds a golf club with one hand? It's a metaphor for the one-handed person that has to. You guys don't understand my art. You guys do not understand my art.
34 yards. 34 yards.
Oh, that's what that is.
102.
No one smiles as they hit the ball. I do.
Plus. So 34 T. So do we put salt? No, I don't think it's good.
Did you guys get parametric equations for this? A. How do you go about A? Let me change the sentence. What did you guys get for A? What's your set of parametric equations?
X 34 T.
Okay.
That's
That's in yards. So you had to change this to feet then, right? Or this to yours? Okay, cool. Just filter. So x of t is equal to 34t. And what's your y of t?
Do sine of 38 degrees. We don't use the 45 or the 30. I think we're
34 seems strange. 34 is the cosine of 38 degrees?
Oh. And the cosine of 38 is 0.95, but I don't.
What'd you guys get for the horizontal function?
Well, if you take the cosine of 38.
Perfect.
Would that be 30x or the y axis?
Yeah, sure.
Yeah, there's no x.
Right?
She's trying to get it. Well, x we got over. So I think I'm
30 would be the choice.
She's going like this. Okay. No. It was plus 100.
What'd you guys get for the horizontal? Yeah? What'd you guys get for the horizontal function?
Oh, it's 30.
You guys are theorem and put it like that, but I'm still pretty sure you
I think it's just
Or no.
97.42.
It's 30.
What'd you guys get for your horizontal?
Yeah.
What'd you guys get for your horizontal? Hey, do me a favor. Finish this off, and then we'll regroup on it tomorrow. All right, tomorrow's Thursday. We'll finish this off. Okay. Remember, Psych 101. You look around in the room, you're like, hey, who's shopping? Change numbers. We got some. Let's go get coffee. Let's go get coffee. And it's the most fun part about being in college. It's got to be the most fun part.